approximately 100 kilometers off the coast of Vancouver Island. Roughly 60 miles out into the cold gray waters of the Northeast Pacific, the surface of the ocean offers no indication of structural anomaly. There is no visible crack running across the moving water, no plume of volcanic smoke, and no line of foam to mark a profound dislocation of the Earth underneath. If a vessel were to navigate directly over these coordinates on a calm afternoon, the surface would appear entirely indistinguishable from any other stretch of the sea. Yet 3 miles beneath the keel of that vessel, a slab of solid rock the size of a small country is dropping away from its structural neighbor, sagging downward into the dark along a massive planetary wound that scientists have only recently managed to image for the first time in human history. This vertical dislocation measures approximately 5 kilometers. To establish a clear physical scale, this vertical drop is greater than the total height of Mount Everest when measured from base camp to summit. This unprecedented structural failure provides the first direct empirical proof of a phenomenon never before witnessed by marine geologists, a subduction zone, the primary geophysical engine driving the most powerful seismic events on Earth. Caught in the actual mechanism of its own terminal decline, this definitive discovery was published in the autumn of 2025 in the journal Science Advances by a research team led by geologist Brandon Shuck from Louisiana State University. The data underpinning this analysis was obtained during the 2021 Cascadia seismic imaging experiment, a publicly funded initiative executed aboard the research vessel Marcus G. Langseth and supported by the National Science Foundation. To map this profound subterranean fracture, the expedition deployed a technique known as seismic reflection imaging, which functions effectively as an ultrasound of the planet. The vessel systematically traversed the gray waters of the Northeast Pacific while towing a continuous 15-kilometer cable containing an extensive array of highly sensitive underwater listening devices. By discharging precise acoustic pulses downward through the water column and deep into the lithosphere, the team recorded millions of returning echoes as they bounced off distant geological boundaries and shattered rock layers. The resulting data allowed analysts to slice open the ocean floor with sound, generating a highly detailed three-dimensional cross-section of a tectonic plate in the middle of ripping itself apart. The structural environment where this failure is occurring is exceptionally complex. While popular conceptions of the Pacific Northwest seismic threat often assume a simple, tidy boundary between one oceanic plate and one continental mass, the northern terminus of this system represents a crowded tectonic intersection. Within a narrow span of approximately 300 kilometers, or 186 miles, 4 distinct plates interact: the massive North American plate, the giant Pacific plate, the Juan de Fuca plate, and a much smaller fragment known as the Explorer plate. Because these distinct blocks are grinding against one another in such a tightly confined space, the immense tectonic strain cannot resolve cleanly. The primary manifestation of this unresolved stress is the Nutka fault zone, a broad band of crustal destruction measuring roughly 20 kilometers or 12 miles in width. Rather than a singular hairline fracture, this zone consists of a braided system of highly fractured rock split into 2 dominant strands designated as the Northern Nutka Fault and the Southern Nutka Fault. Across this 12-mile expanse of shattered seafloor, the data reveals dozens of scarps, which are physical steps and cliffs in the solid stone, where the ground has been visibly cracked and offset by active contemporary movement. This zone of active deformation sits precisely at the front door of the subduction zone, defined by a thick, wavering boundary known as the deformation front, where the ocean floor begins to buckle and plunge beneath the edge of Vancouver Island. The three-dimensional cutaway maps reveal a stark structural profile, a vast wall of fracture plunging almost vertically through the entire thickness of the tectonic plate, cutting completely through the 4-mile-thick oceanic crust and deep into the rigid upper mantle beneath it. Along this vertical red wall of rupture, the Juan de Fuca plate continues its relentless advance toward the continent, while the adjacent Explorer plate has stalled, altering its direction of motion and undergoing a process that scientists classify as a future-captured microplate. This divergence in speed and direction is pulling the original system apart, causing the plate to derail car by car like a train undergoing a slow, progressive derailment. Intriguingly, certain sections of this 75-kilometer tier are chattering with frequent low-magnitude seismic activity, while other segments have gone completely silent. In the inversion of traditional intuition, this silence does not indicate stability. It represents a telltale sign that the friction of the joint has been entirely eliminated because the rock has already finished detaching. The ultimate mechanism driving this piecewise termination is a fundamental thermal paradox. Oceanic plates are born at hot spreading ridges and cool as they move toward the graveyard of subduction zones. However, when a spreading ridge approaches a trench, the incoming crust is geologically young, hot, and highly buoyant. It actively resists being forced down into the dense mantle. For millions of years, this subduction engine has generated the megathrust ruptures known colloquially along the coast as the Big One, such as the historic magnitude 9 event on January 26, 1700, which dropped the coastline, created the coastal ghost forests, and sent an orphan tsunami across the ocean to strike Japan. While the slow death of this tectonic machine will take millions of years to complete, the underlying locked fault remains fully loaded with centuries of accumulated pressure, capable of triggering a catastrophic rupture tomorrow. This realization shifts the focus of global hazard modeling from a question of timing to a question of behavior. When the next major rupture inevitably races along this 1,000-kilometer boundary at 2 to 3 kilometers per second, it will inevitably slam into this newly discovered slab tear off Vancouver Island. The critical systemic question that now confronts emergency planners and geophysicists is whether this deep planetary wound will act as a structural firebreak that stops the earthquake cold, or whether the immense momentum of the rupture will leap across the shattered Nutka fault zone, transforming a localized crisis into an unmitigated regional catastrophe. The realization that the tectonic engine off Vancouver Island is undergoing a terminal structural decline introduces a profound analytical challenge to global hazard modeling. In the public sphere, the announcement of a dying subduction zone triggered an immediate instinctive misinterpretation, leading many to assume that a failing geological machine translates directly into a safer coastline. This superficial narrative posits that if the subduction mechanism is shutting down, the threat of the Big One must be cancelled. However, an evaluation of the system through the strict lens of energy budgets and physical mechanics reveals this assumption to be fundamentally incorrect. The primary error lies in a failure to decouple two entirely different operational clocks: the immense span of geological time and the immediate scale of human history. The terminal unraveling of the subduction zone operates on the scale of millions of years, advancing at a rate of only a few millimeters annually. Conversely, the accumulation of seismic strain along the locked interface of the Cascadia margin occurs over mere centuries, recharging a lethal system that discharges every few hundred years. The slow-motion tearing of the lithosphere along the Nutka fault zone does absolutely nothing to alleviate the centuries of accumulated elastic strain currently stored within the primary megathrust interface. The machine is terminally ill on a macrotectonic scale, yet it remains fully loaded and mechanically capable of a catastrophic failure at any moment. To dismantle the myth of sudden safety, scientists must look directly at the physical nature of a traveling rupture. An earthquake is not a static single-point event. It is a dynamic failure that unzips a locked fault line at velocities reaching 2 to 3 kilometers per second, a speed exceeding that of a rifle bullet. The ultimate magnitude of the disaster is dictated by the total length of the fault plane that ruptures continuously. The discovery of the 5-kilometer vertical drop and the 75-kilometer slab tier changes the entire structural geometry that a racing rupture will encounter. Geophysicists are now forced to confront a critical bifurcated scenario when modeling how this traveling wave of energy will interact with the shattered segment boundary. In the first engineering scenario, the 20-kilometer wide band of shredded crust acts as a structural barrier or a geomechanical firebreak. As the rupture front propagates northward from the loaded zones of Oregon and Washington, it encounters the detached silent fragments of the explorer plate. Because the rock mass here has already finished its local detachment and lacks the cohesive friction necessary to store elastic energy, the rupture may find no fuel to sustain its momentum, causing the earthquake to starve and terminate at the boundary. In this specific outcome, the planetary wound serves as a shield that caps the maximum possible magnitude of the event, isolating the northernmost coast from the worst of the energy release. However, the alternative scenario presents a far more severe systemic risk. If the incoming rupture possesses sufficient momentum, the structural discontinuity will fail to contain it. The failure front will leap across the braided strands of the northern and southern Nutka faults, utilizing the localized stress concentrations to unzip the locked segments on the opposite side of the tier. Instead of halting, the disaster cascades, linking disparate fault segments into a singular interconnected megathrust event that blows right through the presumed boundary. This unresolved mechanical uncertainty is what makes the discovery so quietly unsettling for the millions of inhabitants living in the urban corridors of the Pacific Northwest. The open data collected by the Marcus G. Langseth during the Cassie 21 expedition is now being systematically integrated into three-dimensional hazard frameworks to replace the outdated model of a smooth, uniform plate with a highly segmented, tearing architecture. This transition from a simplistic blueprint to a complex nonlinear schematic does not provide comfort. It systematically removes it by exposing new zones of structural volatility. While this shifting map cannot provide a deterministic prediction of the exact day or hour the fault will fail, it dictates the precise parameters of human survival, directly influencing the building codes that engineers enforce and the survival margins that emergency management agencies must calculate. The physical strain is real, the loaded mechanism is active, and the structural limits of the coast are being tested in real time by a dying giant that remains completely lethal. The deeper structural consequence of this tearing plate network extends far beyond the immediate shockwaves of a moving rupture, penetrating into the long-term magmatic and structural plumbing of the continental margin itself. When a tectonic plate snaps across its entire vertical thickness, the resulting 5-kilometer displacement creates more than just a localized cliff on the floor of the Pacific Ocean. The three-dimensional data models demonstrate that this profound separation creates an open pathway through the lithosphere, a phenomenon geophysicists classify as a slab window. Under normal tectonic conditions, a subduction zone acts as a continuous cold, solid barrier that suppresses the upward migration of the deeper mantle. However, the introduction of a vertical tier punctures this protective barrier, allowing the underlying asthenosphere, the hotter, more ductile layer of the upper mantle, to surge upward into the newly formed spatial void. This influx of high-temperature mantle material alters the regional thermal gradient, transferring immense thermal energy directly into the shallow crust. The rock records preserved across global paleogeological sites confirm that these slab windows are highly active drivers of localized volcanic anomalies, fueling bursts of magmatic activity that migrate across deep time in perfect synchronization with the propagation of the lithospheric tier. What is unfolding off Vancouver Island is therefore not a static structural failure, but a fundamental reorganization of the regional tectonic layout. This deep-seated transformation directly refutes the superficial interpretations often circulating within public discourse. The presence of silent zones along the 75-kilometer fracture has frequently been misconstrued by untrained observers as a sign of stabilization or healing within the Earth crust. This narrative assumes that an absence of microearthquakes implies a state of geological rest and safety. An empirical analysis of the system mechanics reveals that this interpretation is a dangerous inversion of physical reality. In a dynamic fault system, seismic chattering occurs precisely where two rock masses remain locked by friction, storing energy like a bent spring while resisting the immense forces driving them apart. The small, frequent tremors are the direct acoustic signal of an ongoing mechanical struggle. Conversely, when a segment of the fault falls completely silent, it indicates that the struggle has ceased because the connection has failed entirely. The silence is the definitive empirical signature of a completed detachment, a zone where the structural beam of the plate has parted ways, eliminating the friction required to generate further microseisms. The quiet zones are the completed scars where the train has already left the tracks, while the noisy zones indicate where the tier is actively cutting through the remaining rock. This structural uncoupling is further accelerated by an inescapable thermal conflict dictated by the proximity of the Juan de Fuca spreading ridge to the Cascadia subduction trench. As the birthplace of the ocean floor approaches its graveyard, the crust arriving at the subduction zone is geologically younger, significantly hotter, and vastly more buoyant than typical oceanic lithosphere. Because this hot crust possesses a lower density, it resists the downward gravitational pull of the mantle and refuses to sink cleanly beneath the North American continent. When one portion of the plate actively resists subduction while the adjacent section continues to slide downward, the severe directional discrepancy generates a concentration of stress that the plate cannot structurally sustain. The Nutka fault zone serves as the natural pair of scissors that systematically cuts this stubborn, buoyant piece away from the rest of the moving plate, allowing it to drift as an independent orphaned microplate. This planetary transaction represents the missing link that finally explains the fossilized microplates discovered by geologists off the coast of Baja California in Mexico, confirming that giant subduction engines do not collapse instantly but unravel through a piecemeal, episodic termination. For the human communities established along this coast, this evolving structural messiness means that the simple map of a uniform hazard is gone forever, replaced by a volatile network of changing limits and newly exposed systemic deficits. The profound complexity of this crowded tectonic intersection underscores a universal challenge in earthquake science, linking the deep structures of the Pacific Northwest to major fault networks across the globe. To fully grasp the nature of this threat, analysts must look toward a parallel hazard that occupies a dominant position in the public consciousness: the San Andreas Fault in California. In the popular imagination, the big one is frequently treated as a singular uniform type of disaster, whether it occurs in Seattle or Los Angeles. However, a comparative structural analysis reveals that these two systems represent entirely different mechanical beasts, and the contrast highlights exactly why the Cascadia slab tier is such a critical discovery. The San Andreas is not a subduction zone. It is a transform fault where two plates are not diving, but rather grinding past each other horizontally. When the San Andreas locks and violently slips, it generates a massive shaking catastrophe that can approach a magnitude of 8. Yet, because its movement is primarily horizontal, a transform fault generally lacks the vertical displacement required to thrust the ocean floor upward and trigger a major ocean-wide tsunami. The Cascadia subduction zone, by contrast, is a dual-threat mechanism, capable of unleashing both violent, multi-minute ground convulsions and a massive, fast-moving wall of water. This specific distinction becomes critical when examining how traveling ruptures behave at segment boundaries. Along the San Andreas, near the town of Parkfield, scientists watch a section where moderate earthquakes recur with predictable regularity, leading to the long-standing theory that a rupture could cascade southward and unzip a much longer, more dangerous segment of the fault that has been storing strain for centuries. This exact mechanism of a traveling rupture jumping across structural gaps represents the core uncertainty introduced by the slab tear off Vancouver Island. The question of whether a fracture behaves as a permanent barrier or a gateway for a larger disaster is a universal puzzle, and the Cascadia tier provides an unprecedented real-time case study of this geomechanical boundary problem. This scientific reality directly collides with another pervasive public narrative: the conspiratorial myth that academic institutions and government agencies are actively hoarding dangerous knowledge and concealing the true scale of the coastal threat from the public. This interpretation collapses when confronted with the actual operational structure of modern marine geophysics. The data revealing the 5-kilometer slab tier was not acquired through a covert classified operation, but through a transparent, publicly funded initiative open to global scrutiny. The Cascadia seismic imaging experiment was funded directly by the National Science Foundation, using public money to deploy the research vessel Marcus G. Langseth into the unforgiving swells of the Northeast Pacific. The expedition was staffed openly by roughly 20 scientists drawn from diverse public universities and international research institutions, working in continuous around-the-clock shifts alongside a professional maritime crew. The entire purpose of this grueling fieldwork was to collect, process, and publish these high-resolution profiles in the open literature for anyone on Earth to read the moment they were finalized. The discovery exists precisely because the structural blueprint of global science is built on a framework of shared data rather than institutional concealment. What this transparent framework has revealed is not a reason for panic, but a mandatory requirement to update our engineering and survival models. By replacing the outdated assumption of a single smooth plate with a highly segmented tearing architecture, the data forces hazard planners to completely recalculate the structural limits of our infrastructure. A blueprint that maps these deep vertical tiers allows engineers to better understand how seismic energy will distribute through the shallow crust, directly dictating how robust a building code must be to protect the millions of people living in the shadow of the fault. The Earth is not running its program to threaten human civilization. It is simply operating under the cold, nonlinear logic of structural loads and tectonic recycling, and our only defense is the unyielding accuracy of our data. The transition from a speculative hazard to a quantified structural reality forces an immediate reassessment of the human timeline along the Pacific Northwest coast. To understand the true vulnerability of this system, one must analyze the precise arithmetic of the last great megathrust event. On the evening of January 26, 1700 at approximately 9 o'clock, the entire 1,000-kilometer Cascadia margin underwent a sudden catastrophic release of accumulated elastic strain. The resulting magnitude 9 earthquake caused vast stretches of the forested shoreline to lurch downward vertically by 1 to 2 meters in a matter of seconds. The immediate marine influx drowned the root systems of ancient cedar trees in saltwater, creating the coastal ghost forests that remain preserved in tidal marshes today as silent biological witnesses. This rapid dislocation generated a massive tsunami that traveled across the open ocean, slamming into the coastline of Japan 10 hours later. Because Japanese historians of the period maintained meticulous written records, they documented a destructive orphan tsunami that arrived out of a calm sea without a localized precursor shock. By cross-referencing these foreign archival records with the tree ring data of the dead wood and the oral histories passed down across 10 generations by the native peoples of the coast, modern researchers successfully reconstructed the exact calendar date and hour of a disaster that occurred long before European settlement of the region. Sediment core samples extracted from the deep ocean floor reveal that these massive events have recurred 19 or 20 times over the past 10,000 years, establishing a crude statistical average of one major rupture every few hundred years. Because 326 years have elapsed since the 1700 event, the system is operating well within its historical window of reactivation. Marine geologists estimate the probability of a major rupture along the southern segment of the zone to be approximately 1 in 3 within the next 50 years. When the locked interface inevitably fails, the ground shaking will persist not for a few seconds, but for several continuous minutes, a duration sufficient to compromise critical infrastructure, bridges, and urban buildings across Oregon, Washington, and British Columbia. Along the most exposed marine corridors, the subsequent tsunami could arrive in as little as 15 minutes after the shaking ceases, rendering electronic early warning systems obsolete and leaving immediate uphill evacuation on foot as the sole viable mechanism for human survival. Sitting directly atop the northern end of this highly charged system is Vancouver Island, positioned precisely where the subduction engine is tearing itself apart. This geographic convergence brings the entire investigation to its final sobering reality. The discovery that the underlying tectonic plate is undergoing an episodic termination does not alter the immediate human hazard. The mechanical loaded state of the fault remains completely separate from the million-year death clock of the subduction zone. The machine is terminally ill, yet it is fully capable of an imminent, lethal discharge of energy. What the high-resolution data from the Marcus G. Langseth provides is not an escape from danger, but an essential correction to our understanding of its behavior. By exposing the 5-kilometer vertical drop and the segmented, braided architecture of the Nutka fault zone, science has dismantled the comforting myth of a simple, uniform boundary. We are left with a far more volatile and structurally complex template, where a racing earthquake rupture will encounter a shredded lithosphere, leaving the ultimate scale of the disaster to be dictated by whether the fracture acts as a barrier or a gateway. This investigation reveals the absolute limits of human foresight when confronted with the slow, non-linear recycling of the planet's shell. The Earth operates under the cold, unyielding logic of physics and deep time, indifferent to the civilizations constructed on its outer crust, and our only defense is to map its structural limits with absolute accuracy before the ground moves again.